So, my name is Steve Girvin. I am a Sterling Professor of Physics at Yale University in New Haven, Connecticut, in the United States. I am a theoretical physicist. I started in condensed matter theory, studying magnets and superconductors and things like that. But about 20 years ago, I switched into quantum optics and quantum computing and quantum information processing. And I work very closely with my experimental colleagues here at Yale, working on these topics. Together, we've developed kind of industry standard architecture for superconducting quantum computers.
That's really cool. So, how did you get interested in research in the first place?
Well, a lot of my friends in college, spent a lot of time worrying about what they were going to major in, but somehow I knew from a young age that I wanted to be a scientist, and I was just very curious about how the world works and so forth. And somehow I knew I wanted to do physics, even though I wasn't completely sure what that meant, but I knew I wanted to do it. And in graduate school, I had thought I was going to be an experimentalist, but in atomic physics. But the person doing that at Princeton at the time was retiring and not taking students. So I became a theorist in condensed matter physics. But in 1999, I had never heard of quantum computing or quantum information, but there was an experiment on the first superconducting qubit by Nakamura in Japan. And I saw that paper and was just amazed that you could manipulate the quantum states of an electrical circuit, and decided on the spot that I should change fields and move into quantum information. So there's sort of becoming a condensed matter theorist was sort of an accident, but switching into quantum information was very intentional and triggered by that experiment.
That's cool. So, could you give us a quick overview of your research, but in terms that are understandable to a high schooler?
Sure. So quantum mechanics is the theory that applies to the world of the very small, electrons and atoms. And it's a strange theory in which particles act like waves and waves act like particles. And we're doing something unusual with it. We're applying it to electrical circuits. And the thing that plays the role of an atom is a kind of artificial atom or synthetic atom, which is, a piece of wire with two pieces of wire that are joined together in a special way with what's called a Josephson junction. And the charges oscillating back and forth in those wires have quantized energy levels, just like the electron going around a proton in the hydrogen atom has quantized energy levels. But this artificial atom is a millimeter across. You can see it with your naked eye, or at least with a magnifying glass. It's macroscopic. It's much bigger than, a natural atom. And because the currents flowing in the wires are moving a millimeter, and it's like a huge atom, it couples very strongly to the electric field in microwaves. And so that strong coupling lets us measure the state at what energy level these atoms are in by shining microwaves on them. And it also lets us detect and count individual microwave photons, because light is also made of particles, even if it's at radio wave frequencies. And those particles are called photons. So we can do many amazing things that are like having lasers shining on atoms, but instead of lasers, we have microwave signal generators that work at frequencies similar to your cell phone. And instead of natural atoms, we have these artificial atoms that we construct in the laboratory, and which are very big. And those artificial atoms become our qubits in our computer. The quantized energy levels of those guys, if we call those energy levels 0 and 1, those become the dates of the bits in our quantum computer. But quantum mechanics has this strange feature that you can be in a superposition state of 0 and 1 at the same time. And that's one of the things that gives quantum computers their extra power.
Wow, that sounds really impressive. Like I can't begin to wrap my head around quantum mechanics.
So even for professionals like me who have been doing research in it for 50 years, I wake up every morning and say, wow, that's really strange. All these things. It's very counterintuitive, but it's
Okay.
the single best tested theory in all of physical science. It's amazing.
Okay, so what do you enjoy most about your research?
Well, it's kind of a dream job that I have. I spend about half my time working with young people, teaching classes and helping them learn and do research themselves, and about half the time doing research and writing grants to pay for graduate students and postdocs so they can do research. And it's just a tremendous amount of fun to be able to keep every day is different. You're learning, trying to learn new things every day. You're not doing sort of the same routine stuff over and over again. Of course, no job is perfect. There's paperwork, there's various things to complain about, but it's really pretty special to be able to do research and teaching for a living. And being able to work with young people who are enthusiastic and excited about learning new things is a wonderful privilege. So it's just a great job.
Yeah, that sounds really cool. So, like in contrast to that, what are some of the biggest challenges that you've faced in research, and also how did you overcome them?
Well, I would say for quantum computing, we're facing very, very big technical challenges. Like we know theoretically you should be able to do all these things and you should be able to build computers with amazing powers using quantum bits instead of classical bits. But in practice, quantum states are very, very delicate and very sensitive to small noise and perturbation and errors that can creep in. So that's been our main kind of frustration, is trying to learn how to protect the qubits so the information that they're storing lasts a long time. Right now, it lasts only a very short length of time, perhaps one, depends on the system, but between 1 millisecond, 1,000th of 1 second, to a few seconds if it's atoms. Whereas, the memory in your cell phone or your laptop will suffer an error, maybe once every 10,000 years or something. It's very, very good technology. So the technology we're trying to invent here is very, very crude. It's a very, very early stage, and we're struggling to make it reliable and able to correct errors that occur. That's a huge problem on which we're beginning to make progress, but it's the challenge that everybody is facing, no matter what type of qubit or system they're building.
Yeah, that sounds challenging. So, I know you went over this a little bit, but were there any pivotal moments in your research career that made you change topics?
Well, yes. So I'm a theoretician. I don't have a lab, but I think about experiments and so forth. And all the direction changes in my life have come from experimental surprises. So in 1980, there was an amazing experiment which later won the Nobel Prize, in which you have a very thin layer of electrons that lives on the boundary between two pieces of semiconductor. and you put it at very, very cold temperatures near absolute zero, and you put it in a very strong magnetic field, and you saw this amazing phenomenon that the electrical resistance, it's called the Hall resistance, took on a value which was universal, which was just given by fundamental constants and independent of the details of who made the sample or exactly what the sample was like and so forth. And it was a complete shock that these ugly looking samples that were hand soldered and, you could see pits and defects in them, and that they would produce this nearly perfect number, this perfect value. Complete shock and surprise. But it was related to the ratio of two fundamental constants. Planck's constant, which is the fundamental constant in quantum mechanics, divided by this electron charge squared. So this was a complete shock, and I immediately started working on that and devoted almost 20 years of my life to thinking about it. There was a second discovery which led to a second Nobel Prize for the discoverers called the fractional quantum Hall effect, where normally you think of quantum numbers like an electron in an orbit around a proton is in orbit number 1 or number 2 or number 3. They're integers, but the quantum numbers in this system were fractions, like 1/3 and 2/5. And that was completely surprising. Unexpected. And it turned out that this quantum fluid of electrons developed very strange properties. It had excitations in it that carried charge 1/3 of an electron. It's somehow as if the electrons, which are point particles and shouldn't be able to be split, were splitting into 3 pieces, each with charge 1/3. And so that was another shock. And I devoted many years to thinking about what was going on there and helped explain, a little bit of one aspect of the physics of that. And then I already mentioned maybe the third big surprise, which was seeing artificial atoms behave like natural atoms. So it's kind of an accidental trajectory of my research career that just depended on happy, unexpected discoveries in other people's laboratories.
Yeah, that sounds awesome. So where do you see your research field expanding to in the future? And like, what do you think are some interesting topics that can be like further explored within like the next 10 years?
Well, we're just entering the era when, companies are building quantum computers. You can log into them online and program them, and you can try, they still don't work super well because we don't have error correction working yet, but you can experiment with your own error correction codes and so forth. So I think we're entering an era where you can start experimenting on programming quantum computers. And I think there are many things to learn and many challenges that we have to overcome, So we need to learn how to make qubits that have fewer errors and then put those together to do error correcting codes, which will make the errors even smaller. And that's a very complicated task that we're working on. And then quantum computers are not so easy to program, and we're not completely sure. We know they have certain powers that are much greater than what we call classical traditional computers. But we don't fully understand what problems are hard or easy if we have quantum hardware. So there's a whole range of topics, and people interested in this field can make contributions, whether they're computer scientists, electrical engineers, mechanical engineers, high-speed electronics experts, physicists, chemists, mathematicians. There are just so many new possibilities and things that need to be worked on. So for myself, I hope to be able to help build a quantum computer that's good enough to perform simulations of quantum systems like electrons in a metal, or these electrons I was telling you about that form these charge 1/3 excitations. We have a theory for that, understanding the quantum mechanics of that, but actually building a simulator for that experimental system in a quantum computer would let us measure things in the simulator that we can't measure in the laboratory in the real system, because we have access to the actual quantum state and we can measure it much better than in the laboratory. That's one of the directions that I'm excited about and hope to move into in the coming years.
Yeah, that sounds great. So I know you like touched a little bit about how you like found your own passion for research, but how would you suggest high schoolers try to find their passion?
Well, you do have to find your passion. It's becoming an expert on this stuff is hard work. And so if it's not fun, it's even harder. It's just very, very hard if you're not passionate about it. So the main thing is to be curious and get excited about something. It almost doesn't matter what it is. Almost everything in every field, there are interesting things, from biology to geology to astronomy and almost any area of physics. So you do have to learn mathematics. You do have to, if you're going into physics, you have to, take physics courses. But the main thing is to be curious, to notice things. How does an electron orbit a proton in an atom? I have a friend who's very famous, what's called soft matter physicist. He thinks about not quantum things, but sort of classical things. And he used to come into the lab and say, well, it was raining today, and I was looking at the windscreen on my car, and I noticed that the raindrops were following each other down little one after the other on the same path. And, then he started thinking about, well, why is that and what's going on? And he was just always curious about how the world works, and became very famous for explaining things like that. And like when you spill some coffee on a table, if you look, when it dries up, it tends to make a ring, and somehow the coffee grains have all moved to the boundary of the ring. And he explained why that was. Just being curious about how the world works makes it much more fun to say, gosh, I need to solve this problem. Then you say to yourself, well, what tools do I need? What mathematics do I need? What physics class or what engineering class do I need to be able to solve problems like this? Rather than just saying, oh, I got to take a bunch of boring classes and then maybe, I'll be able to do stuff. If you're motivated to understand how the world works, it's much easier to say to yourself, oh, okay, I need to learn this tool or this technique or take that class. And I have a purpose for taking that class because it's going to help me solve these problems that I'm very passionate about, wanting to understand how they work.
Yeah. So what traits do you think define a great researcher in their field? And also, what type of traits are you looking for in a potential lab member?
I think this curiosity that I just described is the important thing. And it's a little hard to look for because people have different personalities. Some people are, quiet. They're very curious about things, but they don't talk about it. And you have to be a little careful in judging people. You have to get to know them to see if they have that passion. And you also have to be careful. Some people are very well prepared in high school and for college, and very well prepared in a good college for graduate school. And other people who are equally intelligent and equally motivated, but they didn't have an opportunity to take calculus in high school, or, come from different circumstances. They may not know as much as other people, but it's just a question of preparation. It's not a question of innate ability. So, I grew up in a very small village in northern New York State. There were 5 people in my high school class. And I did not have calculus before I went to college. In fact, I hadn't seen a library really before I went to college. We had a thing called a bookmobile. It was a truck, like a van, and it had books inside, and it would come by every 2 weeks. And you could order books, but I didn't know like what existed out there that I should order, So going to college was an amazing, eye-opening experience for me. So people come from different backgrounds and, it may take them different amounts of time to learn things, but anybody that's passionate about learning and is willing to ask for help when they need help, not just try to do everything on their own, can do almost anything they want in almost any field. I think all children are scientists. They're curious about how the world works and why the sky is blue and why when you're driving in a car, the moon seems to be following you down the road. Unfortunately, in a lot of places, I feel like school beats the curiosity out of you and gets you to focus on studying for exams and other things. And that's not good. So urge you to, maintain your curiosity about the world. And that's all you need to find a research advisor in college and graduate school and be successful.
And then just for our final question, what kind of tips would you give to a high schooler who's looking to go into physics?
Well, there are a number of popular books you can read. Those are useful. One book that I would strongly recommend if you have any interest in quantum mechanics is a little paperback book by Richard Feynman called QED, The Strange Theory of Light and Matter. And he explains quantum mechanics with pictures and words and no equations. And I have to say that even I, as a professional physicist, learned some things about quantum mechanics by reading that little book. It's really, really wonderful. There are different mathematical formulations of quantum mechanics. They're all equivalent, but different looking mathematics and different pictures. And Feynman invented what is called the Feynman path integral picture. It's amazing to me that he was able to explain this picture just with words and pictures on the page with no equations. And it's completely suitable for people at any level starting in high school. So reading things like that is good. Mathematics is the language of physics. It's the language in which we make precise descriptions and precise theories. So it's important to learn lots of mathematics, as much as you can take in high school. Not everybody has opportunities to take many different math courses, but take as much as you can, take more in college. And, physics is an experimental science. I'll say that even though I'm a theorist. It's almost impossible to come up with correct theories just by thinking, although Einstein was pretty good at it, but most people are not. You need to pay attention to how theories work, as experiments work, and how they're hard and how they also make errors and sometimes the results are wrong. And just knowing a little bit about, even if you become a theorist, knowing about how experiments work and having some experience working with your hands is very, very useful.
Okay, so that's all the questions that I have for today, and thank you so much for meeting with us.
Well, it's my pleasure. Thank you for the questions, and I hope have great success in the future.